All right, well, I want to welcome everyone to the Breathe Easy Study Impacts on Ventilation Retrofits and Air and Asthma. Just really excited about this topic. We talk a lot about energy efficiency improvements for our homes, for existing housing especially, but we can't forget about health and air quality, which can, become a problem from energy efficiency improvements if they're solely the only focus. And so we also have to make sure we're addressing air quality and also potential impacts on asthma as well. So I'm real excited about this topic today and continuing this conversation. If you don't know, this session is brought to you by the Green Home Institute. The Green Home Institute is a nonprofit with a mission to empower people to make healthier and more sustainable choices in the places we live. And today I will be your moderator. My name is Brett Little, and I am the program manager here. As with most of our sessions, this is approved for multiple continuing education units, as well as the health pillar under our Certified Green Home Professional designation, and AIA Health, Welfare, and Safety, which may make it applicable to your state-based design or contractor license. Something real cool coming up, we have our 4th annual Residential Net Zero Energy Conference that will be in person for once in Ann Arbor. Following that will be the Ann Arbor Home Electrification Expo event. And as far as the conference goes, there will be a virtual component for those of you very far away. So get signed up one way or another. And you can check that out on our website and get engaged. We're going to be talking to several net zero home builders. And then always a member shout out, a huge shout out to one of our longtime members, Habitat for Humanity. Kent County just built their first all-electric home, and they plan to fully electrify. This is both for not only energy and carbon reduction, but health impacts as well. So we're really excited about their work. You can check that out and more. They're always doing LEED certification. And, that's what our members are doing. So, you can get yourself featured. You can pick up one of these free mugs. We have a few left. Just go to our website, Green Home Institute, become a member, get instant access to all of our webinars and more. And again, before we get started, a huge thanks to our top tier sponsors who are really helping us with health and ventilation. First, I have to bring up Aware. They have devices that can go into homes both as a standalone or built right in during the construction process. And these devices track temperature, humidity, CO2, volatile organic compounds, and PM 2.5 in real time. I have one. It responds very well and can help people understand what's going on in their homes and make more informed decisions to improve. We also have to say a huge thanks to April Air, who's, once you understand the issue, you can then use controls like humidification control, temperature control, air purity, you name it. You can use these controls to help remove those emissions in the house. And then finally, dilution, right? Panasonic has so many ventilation strategies. Exhaust, supply, balanced, recovery, even smart home ventilation now that actually detects air quality and removes pollutants as they're coming. I've been using it with my range hood. It works great. So you can check all their air quality devices out over at this website here on Panasonic. So with that, I am excited to hand it off to our 3 speakers today, Brent, Insung, and Anna. They're going to introduce themselves and their organizations and take us through this study, and then we'll circle back with some Q&A. So I will hand it off to you all to take it away, and thank you all for joining us.
Okay, great. Yeah, thanks for that a warm introduction and for the invitation to speak today. So I'll quickly introduce the project team, first starting with the Illinois Tech team, of which I'm a part, and then transitioning over to our Elevate nonprofit team. So as Brett introduced, this is what we've been calling the Breathe Easy study. We'll tell you a little bit about the study design and the results so far. And so a quick kind of intro on who we are. So my name is Brent Stevens. I'm a professor and department chair here in the Department of Civil, Architectural, and Environmental Engineering at Illinois Tech. Illinois Institute of Technology, otherwise called Illinois Tech, is a small private university here in the heart of Chicago. So this is just a view of our campus here, if you're not familiar with it, just in the south side of kind of the shadow of downtown. if you're ever at a White Sox game, you get off at the stop that is in between the White Sox and the Illinois Tech campus, our main campus. So we are about 80 plus years old, with a original history dating back well over 100 years. We've got strong undergrad, graduate, and certificate programs, especially in engineering and sciences, as well as architecture and computer science, as well as design, business, and a few more. So I see a number of architects are on. You're probably familiar with our architecture school, but maybe less familiar with our engineering school. And so within kind of that domain, we've got a number of programs centered around the architecture, engineering and construction industry, especially here in the department, but also jointly with the College of Architecture. If you're not familiar with our campus, it's worth a visit if you're ever in Chicago, right? We've got this kind of historic campus. Crown Hall is our crown jewel. This is our building. It's Mies's first building on campus, Mies van der Rohe's first building on campus. So kind of a wild campus that's just tucked here in Chicago. But we do a lot of hands-on work in architecture, engineering, and construction with a number of bachelor's, master's, and PhD programs across all of these domains. We also have a new master's program that we just started jointly between engineering and the College of Architecture, a master of high performance buildings that is literally like half engineering and half architecture, that is kind of just started in the last year or so, in case you might be interested. And within that, I run and co-direct along with my colleague Mohammed Haidir-Najad, who's an assistant professor here. We co-direct the Built Environment Research Group here, where we're focused on energy and air quality in the built environment. And we've got a team of researchers working with us. So you're going to hear from me today, as well as In-Sung Kang, who's on the call and will be presenting, who is a PhD candidate in architectural engineering. A lot of our work centers around kind of understanding indoor pollutants, fate, transport, and control, a big focus on air cleaning and filtration. We also work in building science, measurements and methods. How do you measure this and that? All kind of leading into human exposure and health impact assessments. It's kind of one big track. And then also we're interested in building energy efficiency and energy simulation and building controls as well. So just a few highlights of some of our capabilities here. For example, one of our newest facilities is this large experimental chamber. We've got smaller chambers and a lot of field deployable instruments as well. So with that, I'll now introduce my colleague, Anna McCreary.
Thank you, Brent. Hello all. My name is Anna McCreary. I'm Associate Director of Research and Innovation at Elevate. We're a nonprofit based in Chicago. We do primarily program implementation combined with research. So we have a combination of both research experience with partners like Brent, as well as implementing programs in a variety of different places. Next slide. Our mission is related to both equity and climate. We run programs which support the goals related to ensuring that all households, all families have access to efficient, clean energy for their homes and affordable, as well as we've expanded to a whole home perspective, looking at water efficiency, health, and other related topics. Next slide. And in terms of the number of things that we work on, it's expanded over time. For those of you who are familiar with Elevate, we've grown from a primarily energy efficiency organization to an organization that does many different things. We do community solar efficiency in multifamily and single family buildings, healthy homes, including everything from lead remediation to ventilation and air quality, water affordability and water safety, including lead. We run workforce development and small business development components, community planning, policy, and of course, research and innovation with projects like this one. If you're interested, you can find out more on our website, which we can find out later on. So that's myself and Elevate. Some of our past work on healthy homes, which includes additional work with Brent and the IET team. One of the things that we see in general is that healthy homes is very closely tied to energy efficiency. For those of you who have worked in these areas, there's a variety of different ways. Putting energy efficiency measures into buildings tends to change dynamics that impact people's health. Everything from thermal comfort and temperature to air quality to if you're doing electrification measures, you can remove sources of indoor air pollutants like nitrogen oxides from gas appliances and things like that. There are also, on the flip side, healthy homes measures are sometimes necessary in order to move forward with efficiency. For example, if there's a roof repair that's needed or something else that you have to complete before energy efficiency construction can continue, in an efficiency program or weatherization program. So there's a lot of interconnections between health and efficiency that we've seen in a variety of different research projects. Next slide. In general, in terms of background, health is a key area related to people's homes. The typical statistic that you'll see floating around is that we spend about 90% of our time indoors. That has until recently been in a variety of different buildings for most people. Now that post-COVID, we still have a lot of people that are working from home, spending nearly all of their time indoors, specifically in their homes. And I see somebody's having some audio issues. Let me know if others are hearing that.
We're okay, thanks.
Okay, wonderful, glad to hear it. Regardless, homes have become a center for potential exposure to pollutants in the air and in other parts of the home. So there's a variety of different sources of pollutants and types of pollutants that can come up within buildings like homes, anything from mold or other issues that are related to actually problems in the home. The building materials can produce off-gassing. If you have an air sealed, if you need air sealing, there can be inlets where pests can enter the home more easily. Plus the things that we produce as humans, we emit carbon dioxide when we breathe. Particulate matter can come from dust, plus various other combustion byproducts. All of these things contribute to indoor air quality. And these are things that people get exposed to while they're spending that time indoors. So that's our background. That's why we're working on this issue and hope to improve that by improving our ventilation. Next slide, and we're gonna kick it over to Brent to continue.
All right. Thank you. So now that you know a little bit about us, and our partnership with Elevate goes back just kind of at a personal level. I think they were the very first organization I talked to like 10 years ago when I moved to Chicago, because we had such complementary strengths and interests. And so with that, about maybe 5-6 years ago, the Breathe Easy study was born. So let me give you a little overview to this mostly ventilation-based study with a little bit more as well. So the basics of the study is, first and foremost, it was funded by the U.S. Department of Housing and Urban Development, or HUD, primarily, and then followed up with some co-funding through ComEd, or local electric utility. The overall study design was that it was a 2-year intervention study in this partnership between Elevate and Illinois Institute of Technology. So the study ran kind of 2016-17 through 2020. And the purpose of the study overall was to be the first known, or at least one of the first known studies to evaluate kind of not only indoor air quality outcomes, but also health-related outcomes in a cohort of adult asthmatics. So we're looking at asthma outcomes as well as indoor air quality outcomes when using different types of ventilation systems. So not just introducing a certain type of ventilation, but exploring 3 different common types of ventilation approaches, of which many of you are probably familiar with. One being kind of the broad category of continuous exhaust only, right? You think of this as kind of infiltration through the envelope, continuous exhaust, basically using bath fans, or 1 or 2 bath fans in a home. Another main approach is kind of a intermittent system, cycling on and off with the air handler as it's integrated into the central fan, right? So these are often referred to as a CFIS system, or a central fan integrated supply system, operating on an intermittent basis. It's just kind of a very common approach that we see, not in all parts of the country, but we see in various parts.
Brent, would that also be referred to as a supply strategy, just to clarify on that one?
Yeah, like supply only, no balance. Yeah.
Great, thank you.
Yeah, so you're kind of an exhaust only and a supply only, with the variable of continuous and intermittent. And in those homes, interestingly, with this co-funding with ComEd, we're also able to install more energy efficient fan motors in the furnaces, where in most of the homes where this was feasible. So basically the idea is like, well, hey, these furnaces are going to be operating, let's also get a win-win and install these electronically commutated motors, or ECMs. Maybe you've referred to them or heard of them as BPM motors as well. And so those are 2 categories. And then the third category is kind of the balance system, supply and exhaust with an energy recovery ventilator. There's no energy recovery with the first 2 systems. We could talk a lot about how we came to these these three systems, but they're kind of like big chunks of the ventilation kind of approaches, and they're not exhaustive, but they, no pun intended, but they cover a lot of ground. And so the goal was then to kind of try to inform, when we originally proposed this, ASHRAE Standard 62.2, the residential ventilation standard, to kind of see if there's any versions or revisions to subsequent versions that are needed to accommodate retrofit type scenarios. And then, the big picture is also to provide guidance to homeowners, contractors, builders, and especially agencies like HUD, which is why they funded it, on the disadvantages and advantages of different types of residential mechanical ventilation systems in a retrofits scenario, and especially for both indoor air quality and asthma outcomes. So I've got text heavy slides because we're just kind of describing this 3-year study, but we'll get to some photos in a bit. And so our study details or the goals overall, what we accomplished was installing 3 different types of ventilation systems to meet size to meet ASHRAE Standard 62.2 in each home for outdoor air ventilation rates. And we initially targeted 45 existing homes in Chicago. That was kind of like about the most we could do within the limits of the study and everything like that. Also, in addition to installing ventilation systems at the intervention stage, we also upgraded the central air, the furnace filters, to MERV 10 filters in all homes that were feasible. So a number of homes did not have central heating and air, so we couldn't do it there. And then some homes already had better than MERV 10, so we didn't downgrade their filters. We let them keep their good filters. And everyone else that was below MERV 10 or looked like below MERV 10, we brought them up to at least MERV 10. Like I said, we installed ECM motors in all feasible homes. And then the overall study design and methodology was that we measured indoor air quality and outdoor air quality with a suite of sensors, as well as asthma symptoms over a 2-year period. First, for a year where we didn't do any intervention, it was just a baseline characterization. And then we installed the ventilation systems, we installed the filtration upgrades, and then followed up for another year afterwards. And so we assessed monthly asthma symptoms. We had some baseline and inline questionnaires for some other health-related outcomes. And then on a quarterly basis, we measured indoor and outdoor air quality, which I'll show you in just a minute. That allowed us to also assess kind of the real-world cost of installation. We hired contractors to do this work. And then also the net impact of all this is that it allows us to evaluate the efficacy and the cost of upgrading to these ventilation systems, as well as looking at cost impacts and the energy saving impacts that upgrading furnace motors can do in a number of these homes. So kind of looking for a win-win type of strategy. So here's kind of an explanation of our 3 type of systems. I remember we initially targeted 45 homes. At the end of the study, we were able to get 40 homes completely finished through the study. We got 41 homes through the first year, a few dropped off, and then we kept 40 throughout the end of the entire duration of 2-year study, which isn't too bad. And so type 1 here is just showing a visualization of a continuous exhaust only system. Like I said, ventilation fans, replaced and or newly installed in bathrooms, achieved to meet continuous 62.2 ventilation rates. And this is not giving any infiltration credit if you're familiar with 62.2. The rationale here is if you look at 62.2 and the calculated CFM, the calculated outdoor airflow rates, they're actually not that high. It's a minimum standard. And so we actually just said, look, the literature, in North America and in Europe shows that ventilation, can improve health. So let's add that on top of whatever baseline infiltration happens in the building. So these are kind of ventilation boosts, if you will. And so we ended up with 13 homes in this category. Type 2 here is shown with a central fan integrated supply only system that runs intermittently when the air handler comes on. These are also timed though. If the air handler didn't run, that it would operate like a third of the time, 20 minutes out of every 60 minutes. Type 3 here is again the continuous balance and supply. So 15 homes ended up in the supply only category. And then continuous balance supply and exhaust with an ERV was another 12 homes. Many of these were independently ducted, meaning the contractors ran their own ductwork, in these homes, but that wasn't always possible nor advisable. So some of these are also ducted into to the existing air central ductwork. So it's kind of a lot of confusing configurations, but we ended up with 12 homes in this category, and then a number of ECM motor replacements. And I want to stop here and also acknowledge a number of ventilation system and filter manufacturers that made this study possible. So some were actually already mentioned, but Renew Air, Panasonic, Broan, and April Air each donated a whole host of equipment to make this happen. So you're looking at kind of real world installations, and we were able to work with engineers and the teams there to make sure that our contractors were installing these, appropriately. And also to thank you to Texair Filters for donating the MERV 10 filters. So moving on into kind of data collection, we had kind of these two main lines of data collection, right? One is asthma outcomes or kind of health related outcomes. For these outcomes, we used monthly asthma surveys using this kind of validated survey instrument called the Asthma Control Test. It's actually a trademark tool. You have to purchase this little list of questions or a license to use it. And that generates an asthma control test score, an ACT score, not that kind, but a different kind, not for school, but for asthma. And basically it's a 5 to 25 point summary score on questions like, did you have to use how often do you have to use an inhaler? Do you have trouble breathing and that kind of thing? And so this 5 to 25 point metric, basically, if you get a 25 on your ACT score, you have very well controlled asthma. So, highest you can get. If you have a 5, you have very poorly controlled asthma. And so generally the literature shows a cutoff point of about 19 is the score, above which your asthma is considered controlled and below which it's poorly controlled. And then we also did this suite of air pollutant monitoring, like I said, both indoors and outdoors. So it's really important to characterize outdoors at the same time as indoors, especially because we were interested in how ventilation systems impact both indoor air quality that comes from indoor sources and that comes from outdoor sources, because pollutants outdoor pollutants are kind of treated differently by each ventilation system type. Right. Some of them are filtered at the outdoor air and some of them are unfiltered to the building envelope, for example, in an exhaust only system. And so for this monitoring, we kind of combined we built this kind of suite of sort of medium grade, research grade equipment, not low cost sensors, but not $100,000 sensors, because we needed to duplicate these such that we were always running 4 of these at a time, pretty much in the field. So each home received 4 quarterly, approximately week-long monitoring visits where we deployed indoor and outdoor air quality sensors to record at 1 or 2 minute intervals per sensor, just over time for about a week. We would take that away and move on to the next home and come back the next quarter, come back the next quarter, come back the next quarter. Then the intervention happened where they got the ventilation system upgrades and also the filtration upgrades. And we did another 4 quarterly week-long visits. So we're able to get kind of snapshots of seasonal indoor and outdoor air quality at most homes, both pre and post ventilation system intervention. And we measured formaldehyde using a little passive badge, just indoors. We measured carbon monoxide using a very low-cost sensor. Carbon dioxide using kind of a good mid-grade sensor, nitrogen dioxide, NO2, ozone was kind of a lower cost sensor, a little inaccurate. The NO2 sensor was solid. And then also particulate matter, size resolved particulate matter between 0.3 and 10 micrometers, which we're able to use to estimate metrics like PM1, PM2.5, PM10, if you've heard those terms. We also monitor temperature and relative humidity indoors and outdoors to track, the impacts of these systems on environmental conditions. And then we also had co-location calibration of these sensors, because we've got all these sensors that deployed out in the field. Up here on the top, you can see these are all put in an indoor instrument case, kind of a rolling toolbox that could be locked with air inlets on the side, all the monitors here, and then there's a battery backup so that they never really ran out of power, even if there was a power surge. And then all the instruments are also placed in a deck box, is what we came up with to hide these instruments. Lock them. Every home had some kind of power that we could get outside, so we never had to deal with power issues too much. This also had a battery backup. And I'm happy to report that not a single outdoor box or indoor box was stolen in in a 2-year project. And yeah, so since all these were deployed in the field, we also returned them to the lab for quarterly co-location calibration so that we could just see how they were performing over time. And so here's just a couple of pictures of our deployment. You can see hauling. This is with Parham Azimi, who was initially a researcher on this and now is a researcher at the Harvard School of Public Health. We can see us carting these boxes around. Here's a picture of Insung installing one of these in the hallway. We also, he installed some, we're getting some dinging from people. I'm not sure what that's about. Also installed some plug load data loggers on the powered ventilation systems that were installed in the mechanical units or in the mechanical rooms. You can see those here. We also kind of, what I didn't mention is we also did a home assessment with Elevate's research team kind of at one point early in the study where we measured things like exhaust fan flow in a bathroom exhaust where we could. We had some loggers to monitor runtime of the systems of the furnace and heating and cooling systems and central systems. We also had some anemometers, little wind speed, airspeed monitors that were installed on the exhaust fans in the bathrooms to get a sense of how often, you know, those were operating. So we kind of got this sense of baseline kind of detailed home characteristics, and then kind of indoor air quality and HVAC monitoring over time, as well as monthly asthma surveys. In addition to some kind of baseline and inline surveys of demographics and other health related outcomes. So that's the net bulk of that. We're still publishing a lot of this work. We've published the main paper, like summarizing the study, but all the health outcome publications are still in the works. So with that kind of long intro to the study, I'll turn it back over to Anna to get into some of the results.
Thank you. And the first thing we're going to talk about is the actual installation process for ventilation systems, which is more complicated than you might hope. Many of the homes in our study were older homes. We had a lot of historic Chicago bungalows that were built about 100 years ago right now. So as you can imagine, these homes are in a variety of different conditions with a variety of different existing systems that we needed to accommodate. So we'll go to the next slide. The first thing is that the intention for assigning ventilation systems to homes was not to have any kind of bias or intention behind which homes got which ventilation systems, but because of the existing equipment in homes, it wasn't possible to truly randomize which home got which system. So the actual assignments for the 3 groups into each home was based on, first of all, feasibility. Certainly, you can't install a central fan integrated supply system if you have no central air handler. If the home either has electric heat or has a boiler system and no air conditioner, which is common in many Chicago area homes. So that's the first thing. The expected cost is another piece of it. If the home had some characteristics that meant that one of the systems would have been extremely costly to install, then we would have gone with a different system. Other home characteristic issues were things like, for example, the ERVs themselves are physically quite large, and in some homes there was literally nowhere to put them. Historic Chicago bungalows are a little bit on the small side, and they might not have had a good place that you could put a large piece of equipment like that. So there's a lot of different considerations that went into it. The final piece was that some homes, if there was an existing concern like a mold issue or asbestos that didn't look like it was fully contained, then we aimed more towards pressurizing the home in order to help minimize the risk from those particular issues. And after all of that, we went with contractor recommendations and a desire to balance the groups approximately as much as we could in size. So the final breakdown of the systems you can see here in the chart, we had, as noted previously, 15 homes were in the central fan integrated supply system group, whereas we had 13 homes with exhaust only systems and 12 homes that received the balance systems with ERVs. We put them into 2 columns here because where possible, we also installed the electrically commutated furnace motors to increase the efficiency of the furnaces while we were in those homes as well. We can go to the next slide now. A few of the things that we learned about the system installation is, I've already mentioned a few things. Some of these systems are literally not possible to install in certain homes. The ERV has nowhere to go. There's no place to put it. You're not going to put it in people's living spaces, so you're not going to install that system. in addition to those sorts of learnings, we did have some takeaways related to the skills that contractors need to do this kind of work in existing and sometimes older homes. So of course you need to have your basic contractor skills, your HVAC system, those kinds of things. In addition to that, we found that homeowner education and coordination was a very strong need. So while we were working with these homeowners, of course, they called us for questions. We had quite a few homes, 9 homes here, that needed follow-up visits, either to address minor issues or make slight adjustments to the ventilation systems, or just to educate people, just to confirm the systems were operating as intended and that we needed to talk through them. We also had a lot of calls talking through, the homeowners would call us, oh, it feels a little bit cooler, or we're not sure about it. A few people had some concerns early on. They ended up very happy with their systems overall over time, but there's an adjustment period. And it's really helpful if contractors doing this kind of work can be prepared to educate as they go. There was also one home that experienced a more significant issue and actually ended up dropping out of the study because of this. In this case, there was a misalignment between the ductwork of the system and the ductwork that it was intended to be. So this was an ERV system that was originally installed. And because of this misaligned ductwork, it was actually bringing unconditioned air directly in the living space. And the homeowner unfortunately didn't tell us early enough to address it. So they turned the system off and then continued the study for about 6 months. They tried it again in the summer, and in the winter when it was installed, they were getting very cold air. They turned it off. They turned it back on in the summer, and we're getting very hot and humid air naturally because that's what was happening. And then they called us and said, "No, I'm not going to continue." So of course that's fine. We took the system out. We did what was necessary to address this, but this just highlights that it's important to have that follow-up, to have that education, to make sure homeowners know what to expect, that they might experience slight things that they notice in either the air quality or the freshness or how it feels, or maybe even they might notice slight increase in draftiness, but if it's significant, then that's a problem and they should call. So there is an element of needing to work with homeowners closely. We can continue to the next slide and pass it back over to Brent to talk about our wonderful photos here.
Yeah, so followed on that, we just wanted to provide a little bit of photographic, insight and evidence of what our contractors were doing and how important it was to, find somebody who could kind of do a range of work and understand a range of things. So over here is just an example of a bathroom exhaust fan installation. Fairly straightforward, but a number of homes required exterior penetrations. Of course, a number of these systems, they all require some kind of exterior penetration. And so just kind of getting homeowners that are on board with doing that, and also contractors that can kind of really communicate with the homeowners well, is important. Here's an example of our, I'm sorry, this is mislabeled wrong. This is not for the CFIS system. This is for a ERV system, right? A balanced, independently ducted system. So for something like that in a retrofit scenario, if you're lucky, right, you could kind of run ducts through a crawl space and a basement or an attic space, but we usually weren't all that lucky. And so we would have kind of light construction, upwards to kind of removing some drywall and installing ducting. Very hard to do multi-point supply and or exhaust in these retrofit scenarios, especially within kind of the cost constraints that we had. This is for HUD, right? It's not necessarily kind of a and it is for retrofit scenarios. So we had cost constraints, right? And so our contractors also had to work with homeowners to kind of do this light construction, patch, paint, come back, or patch and come back and paint, and that sort of thing. So we were very fortunate to work with a team here called Nick and Eddie Construction, who is kind of a one-stop shop that we kind of learned. Luckily, Elevate had experience working with them. I've had a number of experiences here where you have to. Contractors won't do everything. They'll only do the mechanical part, but won't do the electrical part, or they won't do the drywall part. And so we really had to find somebody who could just do all this in one stop and not kind of hand homeowners off and so forth. So just a couple more pictures of ERV inlets and outlets here on the right. Again, having to penetrate through brick and these older homes. And here's just an energy recovery ventilator system installed in a basement type space, below the floor here. one thing we just ran into a lot is feasibility issues, systems just too big to fit in certain areas and so on. So yeah, we really set out to try to randomize as much as we could. And we basically gave the contractors a list of, if you could do it, give this home this system. And they often had to deviate. And our goal was just to say, well, if you move one into an ERV category from an exhaust category, then you need to move someone into an exhaust category. And so that's how we kind of ended up with this near balanced grouping, but it was not really randomized because you're subject to so many practical constraints in the field. So anyway, just some photographic evidence of that. So we'll turn it over now to Insung to talk through some of the study results to date.
Right, so from now on, I'm going to talk about our findings in 3 folds: associations between residential exposures and asthma, impacts of ventilation systems on IAQ, and impact of ventilation systems on asthma. Next, please. So first of all, when we look at the asthma control test ACT score by demographic factors, including gender, age, race, income, and education levels, there was an asthma disparity among our study participants. So white participants showed significantly higher ACT score than other racial groups, and with a median score with more than 19. On the other hand, the median ACT scores of other groups were below 19, which means that more than half of them were with poorly controlled asthma. And similarly, annual household income more than 75K showed better asthma control. Next, please. With that in mind, I ran logistic regression models adjusted for those demographic confounders as well as clustering effects within homes, because there were some homes with more than one asthmatic participant. And this analysis was to find relationships between IAQ exposure and asthma during the pre-intervention period. So I found NO2 and ozone were significant risk factors for poor control the asthma. For example, odds ratio of indoor NO2 was 4.5, which means that there was a 350% increase in odds of having poorly controlled asthma per 7 ppb increase in indoor NO2 concentrations. And unfortunately, I didn't observe any other significant relationships from other pollutants. Next, please. And then I ran mixed effect linear regression model with all covariates of relevant residential factors. So we looked at how indoor pollutant and indoor environmental factors such as household crowdedness, mold, or dampness were jointly affecting asthma control. So what we found is that exposures to indoor NO2 and mold or dampness were significantly associated with poorly controlled asthma, as NO2 reduced the ACT score by 0.3 points, and mold or dampness reduced the ACT score by 2.7. Next, please. So now I'm gonna talk about the impacts of ventilation retrofits on IAQ and asthma. So this graph is comparing the distribution of indoor to outdoor ratio of pollutants between pre and post intervention period. And we found installation of mechanical ventilation systems reduced gaseous pollutants, CO2 and NO2, by around 10%. And all of the particles, PM1, PM2.5, and PM10, by around 30 to 40%. And like I just got a question, so we measured the particle numbers by using OPCs, which is optical particle counters. And then we estimated the mass concentrations of particles by using the conversion factors and the size of the particles. Next, please. And this time, when we look at the IO ratio by separate ventilation system type, group 3, which is a balanced ERV system, they show the higher efficacy for reducing CO2, NO2, and oil particles. And in exhaust-only system, CO2 and PM1 and PM2.5, which are finer particles, were significantly reduced. And then CFI systems were only effective in reducing particles. So this can be say that given that balanced and exhaust system were running constantly, so this result indicates that constant ventilation could effectively reduce CO2. And then given that balanced ERV and CFI system got filter upgrades to MERV 10, so better filtration was able to capture more particles. Next, please. So next, I'm gonna present the preliminary findings of health impacts. Just by looking at the histogram of ACT score, a greater number of participants had better ACT scores after they got filter upgrades and ventilation systems. And more participants showed ACT scores of higher than 19, which is well-controlled asthma. So next, please. And comparing the average ACT score between pre and post intervention, all participants and each ventilation group, they showed improved asthma control with around 1 point increase. But it should be noted that the minimally important difference of the ACT score is 3 points. So I say it was statistically significant, but the impact was not that big. And we are still working on more robust analysis for the health impacts. I think that's the last part.
That's right. Thank you, Insun. So I'll take the next couple of slides here and just kind of conclude, mention some of our limitations and hand it over to Anna for some recommendations. So, some of the big picture findings that we found, even before the intervention study, we found this kind of valuable, addition to the body of our understanding that, asthma severity was worse even in our participant population of just over 50 and 40 homes among Black and low income participants. We found associations between poor asthma control and higher exposures to a couple of pollutants, especially indoor nitrogen dioxide, NO2, which is pretty consistent with kind of the literature we've seen summarized of late involving gas stoves, NO2 from gas stoves and respiratory symptoms. So we, kind of fall right in line with some of that. We also saw some associations between a measure of indoor ozone, which mostly comes from outdoors, and asthma outcomes, as well as mold and dampness in the direction that you would expect. That was all kind of pre-intervention. Post-intervention, meaning after the mechanical ventilation retrofits and in the homes that got better filters, across the board, made improvements of some kind to indoor air quality as measured, and also led to were associated with some slight improvements to asthma control. So kind of interestingly, in ways that I don't think we fully understand yet, is that the balance systems with ERV were associated with the largest improvements in indoor air quality. This is continuous, balanced ERV systems, reduced indoor-outdoor concentration ratios, which allows us to normalize for any changes in outdoor of CO2. You would expect that by increasing ventilation, NO2, and size-resolved particles as well. So that was the biggest, kind of the strongest impact on indoor air quality as measured. But interestingly, all three ventilation system types, even if they didn't impact those measures of indoor air quality as strongly as others, showed a significant increase in asthma control. And so basically asthma control was improved in across the board, on average with any type of system. And that was a significant difference, which is good. It's significant, but it's a little sort of borderline meaningful, because there is kind of this, it's hard to tell the difference in a 19 and a 20 or an 18 and a 19 on the asthma control score, but that's kind of the range we fell in. So kind of an interesting set of results there. We also learned a lot on kind of the more qualitative and practical side, which is that education, contractor training, and post-installation quality control are really, really important to ensure that people are satisfied with these systems. And like Anna said, they actually were pretty satisfied on the whole. There are a bunch of limitations that are definitely worth noting. A handful of those are shown here. For one is that even with this effort and this large grant to do this, we still ended up with relatively small sample size, especially for the statistical power needed to have a really robust health study. So it's possible that some findings were not significant, even though there was a real effect. From something like this, or vice versa, that you could distinguish with a larger sample size, but we just weren't able to do that. And speaking of larger sample size, because of our sort of intention to do all of these quarterly air quality visits to really capture, differences in indoor and outdoor air quality, we had no control group. So there was no real ability to test for a placebo effect. So every person, every home got an intervention. There was not like a group of homes that did not get an intervention. And then, we could track how they did or did not, have their asthma scores impacted. We also were impacted by the beginning days of shelter in place of COVID-19. So Insung was out there in the field and had about 10% of his field measurements left to do in March of 2020 when the shelter in place order was issued here. So we missed about 20 visits. We missed some other data just through various data collection issues, instrument failure, and so forth. We also relied on self-reported participant responses to surveys and some of their home characteristics. So there's a potential for like recall bias, not recalling events accurately. And then, like I mentioned, we had some measurement errors in some of our indoor air quality monitoring equipment. A couple of our sensors are kind of on the lower end and maybe weren't as useful as we would have hoped for, but such is the nature of some of this field work. So Anna can close us out with recommendations.
Absolutely, yeah. So our top recommendation here is to think about ways that efficiency or weatherization programs can be combined with healthy homes programs and potentially implement these kinds of ventilation measures. So we see that they're beneficial for indoor air quality. They're beneficial for reducing asthma symptoms, improving asthma control. They're also beneficial for equity because of those findings that it's not news that communities of color and low-income households, low-income families are more likely to be experiencing both asthma and worse indoor air quality. They're also more likely to be located in environmental justice communities and neighborhoods with worse outdoor air pollution problems. By ventilating and, of course, filtering to make sure that the outdoor air is not brought in unfiltered, we can mitigate these equity problems in a variety of different communities. So this is the top priority here is to find ways that weatherization programs and efficiency programs can work with these measures. Similar to the way that we did by adding on ECM, the energy efficient furnace motors. When you're working the furnace anyway, it makes sense to install those as well. Second piece of it is workforce development. We know that these are not necessarily simple installs when you're doing them in existing homes, especially older homes. And it's also not simple from a homeowner standpoint. They need to know what to experience and they need to know what counts as a problem. This is the type of equipment that most homeowners are not as familiar with as they are other sort of more common home characteristics. So we need to ensure that there's training for contractors, both in the installations themselves and post-install quality control and in how to educate homeowners as part of the job that they do. And finally, again, just to hammer this point home rather thoroughly here, We've all seen how important indoor air quality is in the time of COVID. It is still the time of COVID. And so this is a great time to continue to educate people about how improving indoor air quality can help their health in general, especially if they have respiratory illnesses or other issues. And we know that it can also help reduce transmission of COVID and other potential respiratory diseases. So this is a top priority right now. So continue on to the next slide. We're just going to close it out with a few more acknowledgements. We've mentioned a variety of these folks throughout the presentation here, but there's been a large list of both people and organizations that have contributed to the project, and we're grateful to all of them. I won't reiterate this too much because I know we're short on time. So we can continue on and close out the presentation here with a few questions as we go. Brett, as you start running the questions, there's one that I answered in the chat that that I thought might see a map. We could pull it up now if that's of interest, or Brett, you could take over and organize our question process.
Yeah, why don't we just have you get directly to that question? Because we still have, as far as the official time goes, we still have some more time, but I know you all are going to stick around to answer some more. So yeah, why don't you just dive into that one real quick, and then we'll move on to the rest. So.
Sure. Brett, could you flip down to the slide with the map that we have in the appendix? One of our audience members asked about where the homes were located.
Yeah, getting there.
Perfect. There it is. And yeah, as you can see, there's neighborhoods across Chicago. We actually recruited predominantly bungalows, ended up in our study, which is a very consistent style of home throughout the Chicago region. That's what we call the bungalow belt, centered around what used to be almost inner suburbs and are now a core part of Chicago. There are bungalows across many, many Chicago neighborhoods. There are these historic homes, and we ended up with over 2/3, possibly more, of our homes were bungalows. So, but all mostly within Chicago.
Yeah, that's right. And I had mentioned in the chat box too that it's not a lot on the west side, but pretty even distribution between the south side. So downtown Chicago's. Oh, are we?
Oh, sorry about that. If you want to reshare, go ahead.
Okay. Yeah. Just in case people, I know some people are from Illinois or may have Chicago familiarity. So downtown is here. So really mostly on the north and northwest sides. You're beyond the Wrigleyville type near north side, and then a bunch of kind of the south side. The stats that I have in front of me are something like 23 Chicago community areas. Chicago's made up of like 77 neighborhoods or whatever. And so we got a good swath of them.
Great. So yeah, we have a lot of questions coming in. We're going to get to those questions here real quick. Before we do, just a reminder, yes, you can rewatch this. Yes, it's being recorded. You can share it with your colleagues, with your friends. Go to our Green Home Institute channel, hit subscribe. You'll get an instant update on the video when it's there, and you can rewatch it and take it from there. For those of you watching this in the future, not right now, on demand, go to our Thinkific platform or GBCI or wherever you're watching this, whatever channel you're on, and make sure to take that quiz with a 10% or an 80% passing rate, and you will receive your certificate. And for those of you watching live here right now, again, you'll receive your certificate from certs@gutenbergcerts.com. Mark that as safe. Check your spam. You'll see it there. And as those questions are pouring in, we're going to get to them. Just again, a huge thanks to our board of directors, our volunteers, our executive director, Jose Reina, and all of our volunteer speakers this year. So grateful for them. And our top tier sponsors who are helping really drive healthier, more energy efficient housing, Mitsubishi, Rheem, April Air, you name it, so many different folks and organizations coming out to keep these sessions going, and all of our over 200 members as well. So yeah, there are a lot of questions here, and I don't know if we'll get to them all, but a lot of great clarifications, follow-ups. One thing I wanted to kind of hone in on here from the beginning and look at was the duct systems and the MERV filtration. So it's going to be a big question I'm going to ask you all. together. But I think this, it's when it comes to green building, we know everything is holistic, and when it comes to our HVAC systems, we know things, you can't necessarily silo things. So what I'm trying to get at is, you had mentioned MERV 10, you had mentioned you didn't throttle back homes with bigger MERV filtration, which is good. But so the question is, why only MERV 10? Why not go further? We know 13 and 16, especially eat away at PM 2.5 much better. I know that from personal data. But anyway, and then on that note, to give you a little bit of credibility here, a little bit of a pass, pressure drops, right? Tell us about how you measured pressure drops, how you evaluated duct leakage. And someone asked a question about duct cleaning. Ducts, a lot of ducts, a lot of these older homes have ducts that are pan through joists, not ideal. So was that corrected? Were ducts cleaned? Were ducts reduced for leakiness? And how did that tie into your choice with MERV filtration and pressure drops? So big question, but hopefully I'm sure you all have some ideas on that one. So
yeah, sure, happy to address some of these. So yeah, so a lot of these are kind of just limits. So no ductwork cleaning was done. Just wasn't part of the plan, and didn't budget for it. As far as kind of the trade-off, why didn't we go with MERV 13, MERV 16? MERV 13 was kind of originally on the list, but it's really tough to get. We didn't have this is a ventilation study, like it's hard to put everything on the table as much as we would like. So in going in and wanting to increase ventilation, we kind of realized we should at least do some level of upgrade / standardization of filtration, but we weren't in a position where we could install 2-inch or 4-inch deep, MERV 13 or especially MERV 16 filters within the budget limits that we had. Could we, should we, it'd be great. It just wasn't part of it.
Any other follow-up to was duct leakage tested, or pressure systems or anything?
We didn't do duct leakage testing. We had blower door tests, but not duct leakage. And these are, fairly leaky homes. So yeah, just kind of another limit to the interventions. I mean, we've certainly had access to these homes long enough that we could have considered doing it, but the invasiveness, all of our invasiveness capital was spent on ventilation interventions.
Right. Was so was the blower door pre and post?
No, it was pre.
Just pre. Okay. And so, talk to me a little bit about I think you explained it pretty well. I guess I was wondering if balanced ventilation without recovery was considered. So like strategies where you have both the exhaust and the CF. And by the way, I've never heard the term CFIS before. I just learned something new, which I'm stunned about. So yeah, thank you for that. But anyway, and maybe I got those acronyms a little, or the letters swapped, which I do. But anyway, did you consider a balanced system without recovery and or a decentral? Because you had talked about how it was difficult to duct ERVs in some cases. So was there a decentral system, ERV system considered at all?
I don't think we really talked much about a balanced non-condition. And part of this is just being in Chicago. One of the real limits to our intermittent supply system is that it was even more intermittent than you would expect. Well, let me phrase that differently. It was even more intermittent than planned because of temperature shutoffs on the high end and especially on the low end, right? So that was straight unconditioned air, something that I've seen, more in the Southeast and so forth. But this is with a powered ventilator to make sure that you get the flow. But and there's issues where you can't really, what we realized with the CFIS system operating intermittently is you really can't hit like ASHRAE 62.2 flow rates because if you were to factor in it's only operating a third of the time, then you got to deliver 300 CFM in a standard home at one point, which is just a lot of outside air to be bringing in. And then, so anyway, so this thing's moving 100, 120 CFM, whatever it's set to when it's operating, but even then it shut down a lot. So the unconditioned stuff that just led to less operation. What is kind of wild is that we still saw improvements even with that kind of in asthma outcomes, small as they may be, in those even those intermittent systems. So I saw that one of the participants, Vicky, brought up a good point that, look, we only measure 4 or 5 indicators of indoor pollution. That's not the only thing that's impacted, both in terms of indoor air quality and non-indoor air quality, impacts. So even our measures of impact, don't capture everything.
Yeah. So to clarify, those asthma studies were self-studies. They had no doctor involvement, and they didn't evaluate potentially for example, a kid's school situation, correct?
Right. Right. But these are all adult participants, but.
Okay. So you weren't evaluating asthma in kids or anything?
No.
Okay.
We had a few early in the study, but it turned out that by the time we got our study population, there weren't enough to do kids there were not enough asthmatic children involved to really do much of a robust analysis there. You had mentioned something about a decentralized system.
The decentral ERVs, the ones that, are just, no duct work required. So.
We actually got a few of these, I think from Panasonic, that they were kind of more of like the kind of large, like if we're thinking about the same thing, like a large bathroom exhaust fan, but with the ERV component.
Yep. That's right? Basically a great way to put it.
Yeah. We looked into them. And I think we had issues with the number that we would need to achieve the flow rates that we wanted to achieve. It seemed more of like if we had taken an infiltration credit or something and we needed less flow, we could do it. So we've considered them, but we ended up not going.
You keep mentioning infiltration credit. So for all the ASHRAE nerds out there, you're talking ASHRAE 2016, 2019? What was your goal?
At the time, it was 16.
Okay. Because I know a lot of people aim for 10, which doesn't have an infiltration credit. So you were actually trying to get these homes up to 16, which is a pretty tall order. So that's I know we struggle trying to get even new construction projects to 16. So you're actually able to achieve getting a majority of them up to 16.
Yeah. I want to see if we have this plot that I could show.
Oh yeah, and I'll let you do that. So
okay, well, let me see if I can pull it up fast enough to be useful.
And I don't want to dismay people who are listening that aiming for 16 is a bad idea. I think it's actually the best idea, but we do find it challenging, especially with what you said, some of these smaller recovery ventilators, which were meant to help with 2010 in smaller projects. We have a project going right now where it just can't get to 16. So,
right.
For those of you who are like, what is he saying? Email me later. I'll send you some information.
I can, let me share that. So this is the paper that we've published so far. We've got 2 others in close to submission. But this is kind of, if you're interested, I would normally point you to our website, but it looks like my research group website got hacked or something. Like it's like not working right now. So the dings that I heard earlier were the tech support from that you probably no one but me heard was a website tech support trying to figure that out. But anyway, this is the first paper that was published last year, just kind of introducing the study and the indoor air quality measurements and outcomes. And so there's a good summary here of basically what flow rates we achieved with the ventilation systems. Here we go, figure 5, versus what we wanted them to be by ASHRAE 62.2. And again, this basically the way that 62.2 works is that like there's been this discussion that if like, hey, if your house is already leaky, you could maybe already almost meet 62.2 requirements if you calculate, if it's leaky enough, you can calculate it. But kind of, and I talked to a number of people in the 62.2 committee and world and so forth, in planning which systems we would specify here. And it just kind of, like I said before, it kind of dawned on us that it's like, in a typical home, meeting 62.2 means you get an air change rate of like 0.25 or 0.3 per hour. And so from an indoor air quality perspective, my thinking kind of switched at that point when we did that analysis, and we're like, you know what, that's not a lot. That's like, there's some associations with respiratory symptoms and so forth in the literature with air change rates that low. So that's why we were like, you know what, let's just boost on top. Let's make that philosophical decision to assume that ventilation we think will be good based on the literature we've seen. So let's add it on top of any leakiness of your home. So anyway, what this plot shows is like the measured ventilation rate on the y-axis versus the calculated 62.2 ventilation rate. Sorry, it's in liters per second, not CFM, but there's a pretty easy conversion there. And so if you look at something like the exhaust only systems, you see almost a straight line in blue, which is what you would hope to see, which is like, hey, this home needs 50 liters per second or roughly 100 CFM. And what did it get? 50 or 100 CFM. Boom, like that's what you want to see. And exhaust only is very predictable because you could modularize it, right? You could, if you need 100 CFM, that could be one big bath fan, or more than likely it's two 50 CFM bath fans, and you could tune it, The balance with ERV is pretty similar, with like a weird outlier that drives a lot of differences, but pretty similar. If you needed 60, you got, 50 or 60. And some of that just had to do with it's just kind of how these things finally get installed in the field, and then we measure the flow and tweak it as best we can. And then the CFIS systems are all over the place, right? Because they're just limited in a lot of ways.
They're on auto, right? They're not on continuous, right?
They're not on continuous, right? And they're essentially, yeah. So and the interesting thing is that because they're intermittent, we tried, you try to oversize it. So an example here would be like, if you need only 40 CFM, which is like 20 liters per second, if I'm doing the conversion right, well, you're not going to put in 20. So if you need 20, you're not going to put in 20 because it only runs a third of the time at best. Right. Maybe more if it's heating and extremely or cooling extremely, maybe less if it's a swing season, or if it's so cold that the temperature shut off. So it's kind of complicated how it actually runs. So you oversize it, but there are limits to oversizing it, right? So if you need 60 liters a second or 120 CFM, well, if it only runs a third of the time, technically you need 360 CFM. Like, good luck finding a powered ventilator on the market that can deliver 360 CFM, and then good luck delivering that into the home. When the air handler is only moving 800 CFM, now you're looking at like a 40% outdoor airflow fraction. Right. We would get some complaints. So that's why you see like no correlation basically between what 62 says you should install, if it was a continuous equivalent, and what we actually installed, if that makes sense.
No, that does make sense. And maybe you had mentioned this. Can you just remind me, was actual utility data evaluated pre and post?
No, we didn't do utility evaluation, partially just because it's, a few reasons, but mostly because it's so variable and messy that it ends up not being that worth it.
Yeah. One thing we know is a hood range, ducted hood ranges obviously play a huge role in controlling some of the contaminants you had mentioned. Especially when you've got gas versus electric, and then also sealed combustion water heaters, and furnaces versus traditional ones. What role and what considerations did you make for, evaluating either combustion analyzation on naturally drafting appliances, sealed combustion, gas versus electric ranges, or gas versus electric water heaters, and hood range ventilation within this study?
Yeah. So one of the things I
Hmm.
mentioned was we did the kind of a home assessment walkthrough, kind of health and safety check. So that it did include in the very beginning of the study, like to determine whether we could recruit them or not. That did include combustion safety testing. So basically, no one was allowed to move forward without some kind of intervention if there was a combustion safety, kind of issue. I know I saw a number of questions about, so someone had asked a question about, do we control for gas versus electric stoves in the analysis? And the answer is yes, we did control for it. And then when we went to control for it, the results were meaningless because like 36 homes had gas stoves and 4 had electric. So like it was almost all gas. So that wasn't that useful. And then questions there, Joe mentioned something very good, right? Like, did you also replace kitchen exhaust or install kitchen exhaust if they didn't have them, given the importance of that source of cooking for particles and NO2 and others? And no, I mean, like I said, it's sort of just a limit to the study. If you were to approach this with like a different budget and a different lens and more whole home sort of approach, we do it in a heartbeat, and make sure. But this is like kind of ventilation on top of whatever they already had. We did ask some questions about how often they we did mark, do they exhaust to the outside, and then 2, do they actually operate them do they say they operate them when they cook, so
you did gather some information about whether it was exhausting and whether they were using it, right?
Yeah, we did. I don't have that data in front of me, but it's buried somewhere.
Sure enough.
Yeah.
Brent, if I recall correctly, I think there were a decent number of homes where they did not vent to the outside, but it wasn't necessarily dominant. It's a pretty common setup in Chicago, whether you have a stove fan, but it vents into a cupboard right above the microwave or something like that.
More common that it's not venting outside, correct?
Honestly, I'm not sure which is more common. But it's not like predominantly one or the other, as far as I know. I would say likely it's more common that it doesn't vent to the outside, but I need to double check that.
Sure.
Right. I'm able to read the something like only a quarter of the homes had kitchen exhaust fans that we know vented to the outside. A number, I forget the exact number, but a number then also had recirculating fans. And then some homes just didn't have any. Yeah.
Well, it might be interesting to peel apart those 3 different, especially from like a PM perspective, to see what you see. Just, might be another, sounds like you're still putting out reports based on the study. So
right.
That might be something to think about. But I had just learned recently, surprisingly, or probably knew it and forgot, or just wanted to pretend I didn't know it. But, I was reading some stuff from Joe Lecibrick, the Building Science Corporation, and something really old, 8 years old, saying, some studies showing formaldehyde isn't really controlled really by increased ventilation at all. What did you see in your study? Did you look at that, whether there was a shift in formaldehyde?
I think I can answer that. So we only measured indoor formaldehyde concentrations.
Right.
And yes, it was reduced. Yeah, formaldehyde was significantly reduced.
It was.
We don't have the results in today's presentations, but definitely, although the accuracy of the measurement is not that great, but we saw the significant reduction in formaldehyde concentrations.
That's right. That's well said. Like we observed this reduction. It's one of our least confident measurements.
Okay.
So, I know the literature you're talking about, it sort of relates to how emission factors from materials would increase under higher ventilation, I think, or like the driving forces change under higher ventilation such that you still get higher emissions and don't see a big relationship. We saw a median decrease of like halved, like formaldehyde was halved, which I don't even doesn't even make sense from a a logical perspective in many ways. But we really don't know much more than that. It's kind of this potentially spurious, potentially real impact.
Yeah, interesting. You all still have a little bit of time to stick around, or?
Yeah, I've got just another minute or two.
Okay. I'm curious then on that front with COVID, and obviously there's some preliminary evaluations coming out about obviously sort of COVID impacts in real time with air quality. We know that if we still don't admit it, COVID spreads through the air. I mean, I guess we still have to kind of remind people of that. But what did you consider, or are you considering looking at these through the lens of whether people caught COVID more frequently or had worse outcomes from COVID in your study versus just sort of maybe the general population in the community within Chicago?
Yeah, that's a good question. But yeah, no, it's not on the table, at this time.
Mm-hmm.
Yeah.
Yeah,
And
I'd
I
like
will
to add
say-
something. So our health analysis, health outcomes has not only asthma control, but we also have a physical and mental health, and also stress.
Yeah.
And for our preliminary results, mental health and stress, they were lowered. So yeah, they did have poor mental health and stress in the post-intervention period.
Mm-hmm.
So I have a plan to include the impacts of COVID-19, because at the end of the day, at the end of our project, the COVID started. So
Right.
yeah, just preliminary plan.
Yeah.
I'm not sure.
Great. Well, that would be, just interesting to see. And then maybe just the last question, what did you see or study with humidity? Any general notes on both, too much or too little?
Yeah, so that was that was also a good question. So we also measured indoor and outdoor temperature and humidity, relative humidity as well.
Mm-hmm.
So for the statistical model, I have to include temperature and relative humidity as confounding variables, or to see the impacts of how temperature or humidity affects not only the IAQ or health outcomes.
And we do, in the paper that I was showing a minute ago, we do summarize it in a table where across the whole study, there was really not a major change in indoor temperature or relative humidity. We saw statistically significant differences, but it's mostly a big sample size, and the differences are so small that they're like largely meaningless. So for example, the median indoor temperature increased by like 1 degree Fahrenheit with the intervention. And it's pretty small, maybe less than 1 degree Fahrenheit. Relative humidity was about 3 percentage points lower, from like 39 as a mean to 36, or actually almost 37, so about 2% lower. So the systems really on net, like on balance, really didn't impact temperature and humidity indoors too much, interestingly enough.
Yeah.
Just to add to that, qualitatively, we did have quite a few participants that noticed when we asked them if they'd noticed any changes in air quality or their homes. They noticed reduced mold smells, reduced mildew and musty smells. They noticed in the winter, the air was less dry and therefore more comfortable, things like that. So there was a lot of commentary on nuances that maybe it was just perceptions, you never know. But people definitely talked about feeling better in terms of their health, as well as noticing improved air quality as related to humidity and related issues as well.
Great. Well, we will leave it at that. Really grateful, Brent, Anna, Insung, for the Illinois Institute of Technology and Elevate, who Elevate, if you all don't know, is doing some amazing stuff. I work with a lot of Elevate folks in different capacities all the time, always having great conversations with them. So if you're looking for services to help with some of these things, I know lots of folks can be reached out to over at Elevate to help assist there. So I just want to give a plug for them and all the great work they're doing. But anyway, I'll leave it at that, but maybe just real quick, where can people go as a reminder to either see this study or follow further updates that come out from it?
Yeah, so I would normally point you to my research group website,
Yeah.
but like I said, it got busted. So send us an email, I guess. I did put my Google Scholar link earlier, and that's a good place to go. And then hopefully we'll get this website thing fixed.
Great, and your contact information is here on the screen, so maybe if someone wants to follow up too, they can bug you for that, right?
Yeah, email any one of us and we'll loop everybody in.
Yeah, well, I'm excited to dig into this, share this study with some folks we're working with, and I'm really grateful for all of your time here, and I learned a lot and had good conversation. So take care, everyone. Have a great rest of your week, and stay healthy, really. So goodbye.
Thank you so much. I appreciate the opportunity, and thanks everybody for joining.
Thank you, everyone.
All right.
So much.
Bye.
Be sure to check out all of our courses available online that you can watch anytime and anywhere to pick up your CEUs. Before you go, make sure to subscribe to us on YouTube to get weekly updates and stay up to date on green building science courses, webinars, and home tours. Thanks again.